Hello and welcome, dear students. Today we are going to discuss the topic Introduction to Oceanography. Oceanography is a scientific discipline dedicated to the comprehensive study of the world's oceans and seas. It examines physical, chemical, biological and geological properties as well as their origin, structure, dynamic processes. As an inherently interdisciplinary field, oceanography integrates principles and methodologies from physical geography, geology, chemistry, meteorology, and ecology to understand the complex systems governing marine environments. This discipline is fundamentally concerned with investigating the formation and evolution of ocean basins, the mechanics of ocean circulation, and the interdependent relationship among variables such as temperature, salinity, and density. It systematically analyzes observable phenomena and underlying processes that characterize the marine realm. Oceanography is the integrated scientific discipline dedicated to the study of world's oceans. Its scope encompasses the systemic analysis of bathymetry and morphology, which involves mapping and delimiting ocean extent, depth, and seafloor topography. The discipline investigates the physical and chemical properties of seawater, which includes decomposition, thermodynamics, and fluid dynamics, diversity, ecology, adaptation of organisms within the marine environment, and the applied study of the sustainable utilization of the marine resources, assessing their potential and environmental implications of their exploitation. This multidisciplinary framework synthesizes geological, physical, chemical, and biological sciences to develop a holistic understanding of the ocean system. The term oceanography is etymologically derived from the Greek words okeanos or okeanos, which referred specifically to the sea beyond the Pillars of the Hercules, that is the North Atlantic, and graphein, meaning to write or to describe. Thus, its literal construction implies the descriptive recording of the ocean. However, contemporary scientists recognize this original definition as inadequate to encompass the full scope of the modern discipline. While observation and description remain foundational, oceanographic science is fundamentally analytical and synthetic. Practitioners employ advanced scientific and mathematical methodologies to investigate mechanisms, to interpret complex interactions, and construct predictive models of oceanic processes across physical, chemical, geological, and biological domains. Consequently, the term oceanology, with the suffix logia, meaning the study of, is often considered a more precise etymological description of this rigorous process-oriented science. However, despite its etymological imprecision, oceanography remains the dominant and institutionalized nomenclature. Its sustained usage reflects historical entrenchment within academic literature, scientific discourse, and Western tradition of the physical science, where it has become the conventional identifier for the field. This historical development of our understanding of the oceanic dynamics extends well beyond the modern scientific era, rooted in the millennia or empirical observation by maritime cultures. Long before the advent of the instrumental oceanography, knowledge of currents, winds, and tides was acquired and applied. Examples include Polynesian navigators conducted trans-Pacific voyages circa 4000 BC, Panthea Atlantic exploration in 325 BC, Arabic traders utilizing the monsoon-driven reversals of the Indian Ocean, and the Vedic Samaveda 2000 to 1400 BC describing the lunar and solar influences on tides. This pre-modern expertise derived from lived experiences and survival at sea constitutes a significant epistemic foundation often underappreciated in contemporary instrumentation-focused oceanography. The modern European oceanic paradigm emerged from the age of discovery initiated by the voyages of the Dias, Columbus, da Gama, and the Magellan in the late 15th and early 16th centuries. These expeditions, which established the first global trade networks, were fundamentally reliant on the practical mastery of wind patterns, such as the trade winds and westerlies, and the powerful western boundary currents of the Atlantic and the Pacific. This era of exploration was subsequently succeeded by the systematic scientific inquiry in the 18th and 19th centuries. Purpose-led expeditions, such as those commanded by James Cook, began incorporating systemic data collection. The voyages of HMS Beagle with Charles Darwin provided seminal biological and geological observations, while the Ross expedition systematically charted polar regions. Pioneering figures like Edward Forbes investigated the bathymetric distribution of marine life, and others, including Edmond Halley and Benjamin Franklin, produced foundational charts of the atmospheric and the oceanic circulations, such as the Gulf Stream. This transition marks the shift from exploration for trade and territory to deliberate the methodological study of the oceans as a scientific entity. The history of oceanography has not always been the gradual and systematic development of body of thought. Rather, bold concepts and opinions have often burst onto the scene, necessitating critical re-examination of the wisdom of the past and stimulating the fresh insights into the working of the oceans. This evolution can be demarcated into three broad overlapping stages. The era of exploration and description. This foundational phase was characterized by the endeavors of early mariners and natural philosophers. Their primary contribution were geographical, focusing on the charting and extent of oceans and continents and documenting basic observation of surface phenomena. The another stage is the advent of the scientific inquiry, marking a shift from description analysis. This stage involved the first deliberate application of the scientific method to ocean study. This period saw the initiation of dedicated research voyages aimed at understanding the physical and chemical properties of seawater, its circulation and its biological inhabitants through systematic measurement and sampling. The next phase is the modern technology-driven discipline. This contemporary phase, often associated with the 20th century, is defined by the widespread application of the advanced technology, the adoption of an interdisciplinary framework, and large-scale international collaborations. Its inception is frequently traced to expeditions such as the German Meteor Atlantic cruise, which exemplifies the use of sophisticated instrumentations for precise systematic measurement of the oceanic physical and chemical properties. This era is further distinguished by the establishment of the dedicated Marine Research Institute and the coordinator of the major multinational programs such as the International Decade of Oceanic Exploration and the successful scientific ocean drilling program such as the Deep Sea Drilling Project, which was around 1968 to 1983, and the International Oceanic Discovery Program around 2013 to present. Current research is increasingly characterized by reliance on remote sensing, autonomous vehicles, and robotic systems. So far as contemporary oceanography is concerned, it is a data-intensive, globally networked enterprise. It increasingly utilizes remote sensing, autonomous vehicles, and robotic systems critically. The field now conceptualizes the ocean as a dynamic, integral component of the Earth's system, intimately linked and influencing the atmosphere, cryosphere, lithosphere, and biosphere. The holistic perspective underscores the study of ocean health as a fundamental understanding planetary process and sustainability. Oceanography is classically organized into four interconnected subdisciplines. It investigates the physical properties and the dynamics of the seawater, including temperature, density, salinity, and pressure. It analyzes fluid motions such as waves, currents, and tides. This branch also studies energy transfer and interactions between the hydrosphere and atmosphere of the Earth. This branch examines the composition of the seawater chemical and the biogeochemical cycles that regulate the distribution of the transformation of the elements and compounds within the marine systems. This includes the study of dissolved elements, nutrients, gases, pollutants, and their interaction with the biological and geological processes. This branch explores the topography, structure formation, and the evolution of the ocean basins. This encompasses study of seabed morphology, plate tectonics, sedimentology, and the paleoceanographic record of the Earth's history. So far as the ecology, that is the biological oceanography is concerned, it analyzes the organisms inhabiting the marine environment, their life histories, interrelationships, and adaptations. A central focus is on biological productivity, trophic dynamics, and the ecological processes that sustain marine ecosystems. Here the question arises, why we study oceanography? The academic pursuits of oceanography is driven by matrix of interrelated imperative that extend beyond disciplinary specializations. While foundational for oceanographers, marine biologists, and environmental scientists, its principles are integral to numerous scientific and applied fields due to the ocean's central role in the Earth system. From a geoscientific perspective, the oceans are a primary driver of global climatic regulations and a critical archive of paleoclimatic data, making oceanographic knowledge essential for climate science and modeling. Economically and industrially, it underpins the sustainable management and extraction of marine resources, including fisheries, aquaculture, and hydrocarbon reserves, as well as the development of marine renewable energy from wind, wave, and tidal sources. The oceans also constitute the principal conduit for global maritime trade and transportation, necessitating a detailed understanding of nautical science and logistics. From an applied perspective, oceanography underpins the sustainable management and extraction of marine resources. This includes fisheries science and aquaculture, hydrocarbon exploration, and the development of marine renewable energy technologies. Furthermore, principles of physical oceanography are essential for navigation and maritime operations, which remain crucial for global trade and transportation. Ultimately, the discipline addresses a fundamental human curiosity about the planet's last great frontier, transforming a sense of wonder into a structured inquiry that reveals the processes governing the marine environment. Oceanography serves as a critical societal and scientific role by elucidating the ocean influence on global systems, resource availability, and human enterprise. Oceanography provides critical framework for understanding the ocean's function as a fundamental component of the Earth system, with the significant implications for global climatic regulations, biogeochemical cycles, and ecosystem integrity. Oceanography is a discipline of significant applied relevance underpinning critical socio-economic and geopolitical dimensions of human interactions, the marine environment. This important manifests across three primary domains. Number one is the provision of ecosystem goods and services. Oceans are a vital source of protein, supplying fish, shellfish, and algae that support global food security. They also provide raw material for industries including salt for chemical and culinary uses and bioactive compounds from marine organisms for pharmaceutical and biomedical applications. Furthermore, oceans are the primary source of atmospheric vapor, driving the hydrological cycle and influencing global precipitation patterns. Second is ocean as a biogeochemical and nutritional system. The ocean functions as a primary source of nutrition, supporting global food security through fisheries and aquaculture. Consequently, there is a significant scientific interest in oceanic biogeochemical processes that regulate primary productivity, the weather of the ocean, unlike terrestrial agriculture, which depends largely on the atmospheric conditions. Marine productivity is directly fertilized by oceanic process such as upwelling nutrient cycle, internal mixing, which governs the distribution of the essential nutrients along the oceans. Third is ocean as a domain for human activity and infrastructure. The marine environment is a vital space for human economic and recreational activity. This includes the construction of the coastal and offshore infrastructure, global maritime transport, subsea resource extraction, and a wide variety of recreational pursuits. Understanding the physical processes that impact these activities, specifically wave dynamics, wind patterns, ocean currents, and thermal regime, is therefore essential for safe operation, engineering designs, risk management, and sustainable use. Fourth is the ocean as a climate and meteorological regulator. The oceans are fundamental component of the Earth's climate system. They regulate global and regional weather patterns by storing and transporting heat, modulating atmospheric moisture content, and influencing the development of extreme meteorological events, including storms, hurricanes, and typhoons. Research in IRC interaction focuses on quantifying the fluxes of heat, moisture, and momentum across the ocean-atmosphere interface, as well as the ocean's role in heat redistribution and climate variability. This knowledge is indispensable for accurate weather forecasting, climate modeling, and understanding long-term climate change. The word ocean constitutes the planet's primary thermal reservoir, absorbing, storing, and redistributing solar energy via meridional, overturning, circulation, and surface current system. This oceanic heat transport is principal modulator of global and regional climate patterns. Consequently, the precise modeling of oceanic atmosphere interaction, sea surface temperature anomalies, and the thermohaline circulation is essential for advancing the accuracy of climate projections and dynamic weather forecasting. Number fifth is structure and function of the marine ecosystem. Oceanic environments host complex biological communities structured by physicochemical gradients. Oceanography investigates the trophic dynamics, primary productivity, and the habitat heterogeneity that sustain marine biodiversity. This research is foundational to comprehending the biogeochemical cycling of elements and the ecological services provided by marine ecosystem. Number 6 is the conservation of marine biodiversity. So the application of oceanographic principles is integral to conservation biology and ecosystem based management. Studies of species distributions, population connectivity, and responses to environmental stressors inform the designation of marine protected areas, the development of species recovery plans, and the strategies for preserving genetic diversity and ecosystem resilience in the face of anthropogenic change. Number 7th is the hazard mitigation and strategic security. Oceanography is crucial for assessing natural hazards. The study of submarine tectonic and seafloor dynamics enables the monitoring and prediction of geophysical events such as earthquakes and tsunamis. This knowledge also underpins the strategic and political importance of oceans, influencing maritime boundaries, resource rights, security policies, and international governance, making the seas a domain of both cooperation and geopolitical contention. Number 8 is the environmental monitoring and impact assessment. Oceanography employs a suite of in situ and remote sensing technologies for the continuous surveillance of marine environmental health. This includes tracking pollutants, for example, plastic debris, chemical contaminants, assessing eutrophication and hypoxic zones, monitoring oceanic acidification, and evaluating the cumulative impacts of human activities such as coastal development, resource extraction, and climate change. This scientific monitoring is indispensable for evidence-based policy and mitigation strategies. Now, 9th is the economic and resource base. The ocean is a major repository of extractable resources. Continental shelves and the deep seabed contain substantial deposits of hydrocarbons and mineral deposits critical to modern industry. Furthermore, oceans are foundational pillars of the international economy. In the US alone, 1 in 6 jobs is linked to the marine sector, and ocean-related industries including real estate, tourism, fisheries, and biotechnology generate tens of billions of dollars annually. This economic dependence is geographically concentrated with over 2/3 of world's population residing within 100 kilometers of coastline. So moving to the 10th, global logistic and trade. So far as the maritime routes are concerned, the principal arteries of international commerce, with over 95% of US foreign trade, for example, transiting through ports and harbors, the efficiency of bulk shipping via commercial vessels and barges is indispensable to global supply chain, marking the study of maritime routes, port logistics, and navigational safety a direct economic imperative. In summary, the ocean functions simultaneously as an economic asset, a logistic highway, a biological repository, and a dynamic geophysical system. Its study is therefore essential for informed policy making, sustainable resource management, and resilience planning in the face of environment and geopolitical challenge. Now we will take an overview of the oceans. The Earth is fundamentally a marine planet with the global ocean constituting its dominant surface feature. This interconnected body of salt water covers approximately 361 million square kilometers or 70.8% of the planet's surface, while continental landmass comprises the remaining 29%. The ocean's total water volume is estimated around 97% of the Earth's surface water. This marine domain is not uniformly distributed between hemispheres. The northern hemisphere is 61% ocean, while the southern hemisphere is overwhelmingly maritime, with oceans covering 81% of its surface. The global ocean is conventionally subdivided into 5 principal basins: the Pacific, Atlantic, Indian, Arctic, and Southern Oceans. the Southern Ocean is formally defined as the body of water south of 60 degrees south latitude and circling Antarctica. These basins collectively contain an estimated 97% of the Earth's surface water, with the Pacific Ocean alone accounting for roughly 52% of this total, which is followed by the Atlantic Ocean with 25% and Indian Ocean 20%. The mean depth of the world ocean is roughly 3,800 meters, a figure that is approximately 4.5 times greater than the average elevation of the continental crust. The mean depth of global ocean is approximately 3,800 meters, a figure nearly 4.5 times greater than the mean elevation of the terrestrial surface. The maximum known depth occurs at the Challenger Deep within the Mariana Trench, which reaches approximately 11,022 meters. The largest basin extends from Antarctica northward to the Bering Strait. Its western boundary with the Indian Ocean is conventionally drawn along line from the Malay Peninsula through the Indonesia archipelago, Sumatra, Java, Timor, along the northwestern coast of Australia, Cape Londonderry, and the southward via Tasmania. From Tasmania to Antarctica, the boundary follows from South Cape Tasmania. So, the oceanography is an inherently multidisciplinary scientific discipline fundamental to understanding the complex dynamics of the world's oceans and their integral role within the Earth's system. By systematically investigating the geophysical origins of ocean basins, the mechanics of thermohaline and wind-driven circulations, and the physiochemical relationship between the variables such as temperature, salinity, the field illustrates the governing principles of marine environments. Oceanography endures as a vital and dynamic scientific frontier. It not only expands the boundaries of fundamental knowledge, but also serves to inspire equip successive generations of researchers to address the profound and unresolved questions concerning the largest component of our planet surface. So, this was all about today's lecture. Hope you have enjoyed it well. Thank you for watching.